Hi everyone. Thank you for joining us to this lecture. I'm honored to be here and giving this presentation. My name is Gal Oren, and I will present my talk about unlocking the potential of large language models for high performance computing code. So that's kind of different than the usual intersection that we hear a lot about, the intersection between AI and HPC. So in this case, we are focusing on how to use those LLMs for us, the practitioners of HPC. Before I will start, I would like to note that all of the work that you will see in this presentation is based on a collection of articles that's been published this year with many collaborators from Intel Labs, Ben Gurion University, Iowa State, and if you want to go further and dig into some of the topics that I will bring up, so please go ahead and read those articles or watch the videos that are already accessible for most of those. I would also like to really thank our sponsors that without their support, this work could never be done. So thank you all. In this presentation, we will go through several topics, as I said, somehow in a linear fashion. We'll start by giving some intro and objectives to our work, specifically why we need LLMs for HPC code, and how it can actually help us. Then we will move to discuss the data, the most crucial part when we address data-oriented problems. And we will present HP Corpus, which is a state-of-the-art collection of HPC-oriented codes. Then we will move to talk about one step before the training, which is the tokenization step. And when I'm talking about the tokenization step, I'm talking about how to change the tokenization step in order to fit it better or proper to the task of HPC codes. And we will present Tocompiler, which is our state-of-the-art tokenizer for compiled oriented codes. Afterwards, we will discuss the pre-training of our new CompCoder model, and we will showcase how we use it for a task of OpenMP classification, meaning at this stage we want to understand if we can properly understand if the code that is in front of us should be parallelized and how. And eventually, at the end of the talk, I will talk about our next steps in this field. So let's start. Well, it's not a secret that LLMs are the new frontier in AI. Those ever-increasing scope models trained on infinite amount of data, and with infinite amount of data representation, and trained on large-scale supercomputers, those massive models can perform enormous amount of tasks given their knowledge fusion. And that ranges from writing poems to coding Python scripts. So that's a common knowledge that we all have about what are LLMs. And this booming trend gave us all sorts of models, as you can see in the graph. If we focus on GPT models as a building block, it's not a shock that early experience with GPT-4 is now considered a spark of general artificial intelligence. Narrowing down our talk to the interest of code operations, those kind of models are getting better and better, doing all sorts of code intelligent tasks, especially when we ask them to do so in our natural language, to act on or generate some code. But when we ask ourselves, can those models work well for HPC code task, we got a little bit confused. I mean, if such tasks target the compiler and the hardware, the task in HPC, and there is no meaning at all to any kind of those natural language semantics, and that's not even a consideration for us besides performance. That's the only thing we need. How general purpose code models like those can even help us in achieving that? Are they even trained to do this? Or they will just act to please our request given such a task without even understand it? So this is a really important thing that prevents people in the HPC community to somehow join this revolution of LLMs, because we are in some deeper level in code understanding and in code actions that are somehow different than what general purpose users do. So if a user that is usually programmed with Python is really pleased with these GPT models because they based on script and they can generate scripts, that's great. But we know that our code is only the facade to what is going to be happen on the hardware, and that's not a thing that is currently well reflected to those LLMs. And if we want to be specific, when transitioning from the general purpose code tasks that we mentioned before, we can now see clearly that the relevant ones in HPC codes are not the same at all. I mean, to take, for example, the problems with that needs data flow graph in order to perform well. Take codes that need AST in order to figure out what exactly is happening in the code. So we clearly understand that this kind of what I called HPC code intelligence is not well reflected in the general purpose code task that we are familiar with. This is why we dug into the code models, the familiar ones, and try to find out what can help us with HPC codes. Our main concerns about those models remained. I mean, can non-HPC languages, which all of those models are trained on, let's say Java or Python, be the baseline for HPC tasks? Are there any relevant large corpora of high performance code that can be the baseline for a pre-trained model? What are the exact downstream tasks for HPC and how we can correlate those with common models? Because just saying code models for HPC, it's too general if we remove natural language and we remain only with model that need to predict code. And is mixing of languages and tasks is even a good way to succeed with HPC LLMs? All of those are open questions for us. When we looked carefully at how those models were pre-trained, we also asked ourselves, are common tokenizers even relevant for compilation-oriented code? What is the relevant model architecture for HPC task learning? Is that models that only based on code with additional AST, with additional DFG? What should be there in the data that you use for pre-training? Also about the architecture, are we want encoder-based models that mostly target classification? Are we want decoder only for generation? Do we want to use encoder-decoder models that will do both but with a higher cost? So all of those are open questions for us. And when we started to understand that we will need to take care of all of those considerations in case we want to create a new HPC-oriented LLM, we also wondered, should we consider other representation rather just plain code? Should we take into consideration AST? Should we take into consideration hardware specs, telemetry of the hardware? Should we be part of the input, only of the test? Can we reduce the size of the input? Can we reduce the size of the model? Can we reduce the time to train? Those are really important questions when we want to create a model for HPC code, but that will also be very efficient for generating this kind of code. And that took us to the conclusion that in the case of HPC LLMs, as we call it, there is no generality. I mean, if someone wants to transform an LLM actually to help with such HPC-oriented task, what we need is scope. Scope is all you need. I mean, we took this phrase and rephrased it, but that's not just for advertisement. I mean, the scope of the LLM is something that also improve the ability to do better verification and validation, to be much more precise on what you want from the model. In what kind of language do you talk to the model? And all of those considerations, which we call scope, are the baseline to the rest of our work. So the first building block of our work would be the HP corpus, this novel HPC code database. When we want to talk about HPC codes, it's kind of a tricky thing. I mean, we used to call to HPC compilers for C, C++, and Fortran, but ever since, in the last decade, we got new languages, let's say Julia. Now that is actually an HPC language, but it's not compilable as C, C++, and Fortran is. So, moreover, when you look on HPC centers, I took here, for example, the Frontier and Aurora, those supercomputers in the national labs. And you look on the portfolio of codes and languages and parallel APIs, you pretty much see that there is a consolidation around C, C++, and Fortran as a high-performance codes and compilable high-performance codes on one hand. And on the other hand, we see that the parallel API mostly rely on MPI for distribution and OpenMP for parallelization. So we wondered why not, if we want scope, why not take in all of those languages? Somehow get all of those codes that are based on those languages and with those parallel APIs, and create a new corpus for those, and that will be able to be the base for the fine-tuning and the downstream task that we have. Let's say downstream task for parallelization would be to distribute code or to parallel code. Another downstream task for HPC code would be a specific task that people in that work with scientific code in C, C++, and Fortran usually deal with. Let's say maintaining legacy code. Let's say optimize some function or replace a code with an optimized function. One can ask, why not to fine-tune given models that have been trained on Python or Java on C and C++ code, and then maybe create downstream tasks for other specific tasks. Why not to do that? And in this really nice and pretty much intuitive research that's been carried by another group this year, they found out that the pairwise similarity between the representation of tokens of all code languages in CodeBERT is distributed really non-uniformly, even in pre-trained and obviously non-pre-trained settings. You can see that while the similarity of tokens for C and C++ is very high, the rest of those languages don't really correspond well, in the pairwise similarity one to the other. It means that the notion that I will take so many languages and try to somehow get a coherent tokenization to all of those, specifically when I want to do a compilation-oriented task, is not a great idea. So that's why we, from here on, decided to do all of our work for Fortran on one hand, and for C and C++ together on the other hand. What you can see here is the data collection that we had for HP Corpus. We used Google BigQuery to practically download most of the C, CPP, F, F90, F95 codes out there. We decided to take all of those and then do other analysis of what there is in it, instead of doing this the other way around. And we really found tons of data. Eventually it's about 150 million functions in more than 300,000 repos. This is an enormous amount of data that could really use us for downstream tasks, but obviously for pre-training. But just using this corpus as it is not enough. If you want to handle specific tasks, and one of our major tasks is compilation-oriented task, the OpenMP program classification, and eventually event generation, you need to understand what there is in it, because this data, this specific data about the parallel API in this case, would be helpful to create the specific downstream task. Now, in this conference, you can hear Tim Axon, which is part of this research, talk about how popular is OpenMP. It's also been published in HPC recently. So we see that MPI and OpenMP are of great importance, that we actually managed to achieve those codes in a way that represent the progression of and the evolution of those APIs over time, which is really important because we know that when you look on those kind of APIs, in this case it's only OpenMP, you know that over time there were major changes in the API addressing completely different task of parallel computing, moving from simple parallel for to tasking, to handling NUMA and SIMD, and eventually, obviously, offloading kernels to GPU. And we also see that in the distribution of the amount of codes in HP corpus. When you look carefully into the results, you can also see that parallel for threadings and vectorization and GPU offloading is really important, meaning that we can use this data in not only for pre-training, but mainly for the task of for the downstream task of generating parallel code. So our next step in this journey is the tokenization. I mentioned that at the beginning of our talk that we were really concerned about the tokenization step in those code language models. We usually see that those models are pre-trained on a mix of languages, let's say Java, Python, and C++ all together. Now, it's really crucial to understand what's happening in this stage during training to understand the importance of the tokenization on the entire model performance. Now, code in this step is all passed through the same tokenizer for all of the languages. Now, this same tokenizer converts the code into individual tokens. And those tokens are converted eventually into a higher dimensional token embedding. Now, these embeddings are then passed into the transformer layers, as you can see that in the middle of the figure. The task of a language model is to take an input and predict the next token. Now, you can see that in the example in stage 2 that we get the chicken walked, and the task of the this decoder-only model is to give us across the road. That's the generation part. Now, to measure how well that kind of model works, we use a compute performance measure that's called perplexity. And you can see at the top in stage 3, the perplexity of different code models and how they performed for different kind of languages. So we see this variety in the performance that we get from those models, and that's what concerned us. And we wondered, is it possible to somehow change the way that the model is being talked and is talking, and by that to achieve much better performances? And by that it means a better accuracy of the predictions. And don't take my word for this investigation needed into the tokenization step. Just look on how GPT and Codex perform this tokenization step. So those examples that you see here are of PyCodes. You can see on the left that in GPT-3, even white spaces are being considered tokens. Now, that's been fixed in Codex, but still you can see that Many times numbers are being divided. Primitives of the language are not intact when they've been fed into the models. So and we in general know that LLMs don't really understand well numbers. Don't really understand well when you intentionally confuse them. And that's why for our own tokenizer or compiler, we wish to maintain the overall code structure, while we also wanted to remove as much as possible of the local semantics that confuse the model. Let's think about an example of a for with ijk. Now, most of the fors have ijk indices. Now, I don't want the model to somehow learn that ijk have a meaning, because next time we will see a for with kjn. Now, that's crucial when we want the model to actually understand what's happening in the code. And to make sure we only keep the functionality of the code rather than the natural language comments and things like that, we use a parser to generate the AST based on the original source code. And we use this tokenized AST in order to enhance the initial source code with the needed primitives. Now, instead of having a variable that have the name of let's say my friend, so instead of that, I can replace this variable with a primitive that says this is a variable and its index is 8. And that will be consistent through the entire given code. Now, in any other code, we will randomize this again and again in order to prevent the model to fixate it on that variable 8 has some meaning, because it doesn't. And the most important takeaway is that compiler has a very small vocabulary. We are talking in the example of Fortran on about 1,000 plus 1,000 locals that we set. It could be also 2,000, let's say, with an additional of 177 primitives that exist in the language. So just a couple of hundred of primitives are used here. And that's in comparison to typical LLM that usually have a vocabulary of 50,000 or more than that. It's a big difference. So to prove that this tokenization actually help us to generate code better in this HPC code setting, we pre-trained from scratch Polycoder, which is a great model for this task, and compared the initial known results of their perplexity as been described in their paper to the perplexity that we get with our model that we called Comcoder, which is practically Polycoder with this different tokenizer. And we notice that we get a huge achievement in performances. Look on the Fortran and the C++ corpuses here. You see that we get almost 1 point of perplexity better than a Polycoder in the case of Fortran. Even in the case of C++, we get better performances. The model size reduced dramatically, and that's mainly can be seen in the case of C and C++, which is a much larger corpus in comparison to the Fortran one. And above all is the time to train, which is the actual money that's been needed to train these kind of models. And you see that we get twice or 4 times the performances of the polycoder initial results. Now that really encourages us, as an empirical results, suggest that we are in the right path to create a model that its scope actually help it to be more precise to our HPC code tasks. Now, when we have this powerful knowledge about what can serve HPC tasks in the case of LLMs, we reach to the, I would say, the final destination, to the actual downstream task. And in this presentation, I would like to present one of those downstream tasks, the OpenMP classification task. The OpenMP pragma classification is the complementary downstream task to the OpenMP pragma generation. The importance of this task is that before you train a model to generate for any kind of a code the needed pragma, you first need to understand if there is even a need for such a pragma. And that's a classification task rather than a generation task. So in this task, we ask ourselves, can we detect the opportunity for parallelization before we actually do deparallelization? We also ask ourselves, what should the variable scope be? I mean, detect if we need variables to be private or in a reduction, and those preliminary stages are crucial to move ahead and perform generation. Our strategy was to look into HP corpus and look specifically for the repos that contains OpenMP. Now, in those repos, we divided the loops that we found there to the ones that have OpenMP parallelization, to the ones that don't have OpenMP parallelization. And the assumption here is that because a user, a programmer, a human, actually wrote these codes, so this programmer already knew where to put parallelization and where not to put it. And those are the positive and negative examples that we used for our classification here. So we divided this classification task so initially we developed this tool called Performer. And what we discovered is that Performer is heavily relied towards local semantics. That was part of the reason why we really wanted to move on to use Comcoder that I mentioned before. But besides Comcoder, we really ask ourselves, can we do better in the design of the downstream task? In this case, of the OpenMP downstream task. And we ask ourselves, can we exploit different code representations, let's say AST or DFG, in order to get better classification? We also ask ourselves, can we provide an extended scope of the code, meaning code before and after the structure block, in order to get a better decision if a pragma should be inserted or not? And eventually, we also ask ourselves, can we move these classification questions into a unified model that will generate all of those at once, because we know that there is interconnections between those three different questions. And eventually, all of those questions are being answered with the development of OMPify. And OMPify showcased much better results in this classification task in comparison to Performer and ChatGPT. And we can also see why we get this kind of huge performance improvement in comparison to ChatGPT. Because ChatGPT will constantly try to give you a prediction to put a pragma there, even though it's not necessary. Meaning the nature of those models as a pleasers is not facing the actual reality of code optimization using OpenMP, which in many times should include the programmer discretion about whether or not the addition of parallelization is actually contributing to performances. And by that, we almost reached the end of this lecture, but I will not leave you without telling you what we are currently investigating further. So the first immediate step, obviously, is OpenMP pragma generation. In this case, we try to generate the entire pragma, but sometimes only the variables. In the cases of parallel 4 and teams distribute, we do this separation between CPUs and GPUs. And I can tell you already that the results are very encouraging. The second one is the MPI SPMD code generation. In this task, we try to generate the variables or the functions or the locations or all of those combined of the MPI needed in order to distribute a program. The third one regards the possibility to rely on a compiled version of the HP corpus rather than just on all of the codes that we gather for the pre-training stage and even for downstream tasks. That's why we, in a collaboration with Iowa State, developed the compcode vet, which enables us in a chain of thought prompting to allow more codes to be compilable using LLMs. Now, that's crucial when we would eventually like to pre-train from scratch comcoder in order to on these codes in order to get much higher validation that the results of the predictions and the generations are actually compilable. The last next step is to take all of that research and not leave it just in Hugging Face or in GitHub or as research papers, and to move it into a tool based on open source tools such as the OpenMP Pragma, and to create some sort of a copilot that will either based on our demand do insert parallel for CPU or offloading to GPUs, or just complete the variables needed based on true understanding of the code and the parallel design of this code to give us the optimum performances when we will compile and run it. And by that, I would like to thank you very much. And please don't hesitate to contact me. Our group is very open to suggestions and collaborations. And I hope that by next year, we will be able to unlock fully the potential of large language models to HPC tasks and codes. Thank you very much.